This is the second lecture on Text Unit 7, which is on molecules and bonding. This lecture is on exceptions to the octet rule. Briefly review the octet rule. We have seen, with the exception of hydrogen, that atoms and molecules like to have an octet, 8 valence electrons, 8 valence S and P electrons, through sharing for stability. We will now discuss molecules which do not, which have atoms in them, which do not have an octet. Naturally, there are exceptions to the octet rule. Two types of exception can occur. Molecules with central atoms with less than an octet, and molecules with central atoms. Again, let me emphasize central atoms with more than an octet. We'll look at the first type first, and then we'll look at the second type. Molecules with central atoms with less than an octet. First case to look at is the case where beryllium is the central atom. Now, if you look on the periodic table, beryllium is in the alkaline earth metals column, so it seems odd that it would be forming a molecule at all. It should form ionic compounds, or it would be a cation. However, there are some strange molecules where beryllium can be a central atom, and it makes sense, I suppose, that if these are strange molecules, they'd have some strange bonding situation. So in general, in a beryllium molecule, the central atoms have 4 electrons from sharing. So for example, BeH2 is actually a stable molecule. A BeH2 molecule has 4 valence electrons, 2 from beryllium, 1 for each hydrogen, and forms 2 bonds. When you stick the 2 bonds in, you're out of valence electrons and you've completed the Lewis structure. The beryllium has only 4 electrons through sharing. Before you go on, or in the presentation, try writing down the Lewis structure of BeCl2 or BeBr2. Again, these are molecules, not ionic compounds. Alright, if you count each of these chlorines contributes 7 valence electrons, beryllium has 2, so the total is 16. If you look at this Lewis structure for beryllium chloride, 2, 4, 6, 8, 10, 12, 14, 16 valence electrons appear. So all the valence electrons are in the picture. Again, beryllium only gets 4 electrons. In other words, one of the lone pairs from the chlorine does not multiply bond to complete the octet on beryllium. There are no double bonds to the beryllium in a structure like this. That's a very common mistake in making Lewis structures. Bromine has the same number of valence electrons as chlorine, so when bromine is the outer atom, the same situation exists. 3 pairs on the bromine. In each beryllium has only 4 electrons through sharing, and likewise the same is true for beryllium iodide. Each one of these molecules has only 16 valence electrons, and beryllium has 4 by sharing. By the way, these 3 molecules are an example of a series of molecules that are isovalent. They all have the same number of valence electrons, and you can see that the Lewis structures are very similar. Alright, moving on, boron compounds also are exceptions to the octet rule. Boron central atoms and molecules have 6 electrons by sharing. 6, not 8. So BH3 is a stable compound. There are a total of 6 valence electrons. put 3 bonds in, and you have the Lewis structure for a stable molecule. Alright, now again, assuming the same behavior for the, on the part of the boron atom, draw a Lewis structure of BCl3 before moving on. I include 2 boron halides in this picture to show you again that they are very similar. There are 24 valence electrons total, 1 from the chlorine, or fluorine, 7 from each chlorine, or fluorine in this picture down here, 3 from the boron. When you draw single bonds from the borons to each of the halogen atoms, and you can complete the octets by putting lone pairs down on the halogens. Note you don't complete the octet for boron. Likewise over here, where the attached outer atoms are fluorine. Lone pairs complete the octets for the outer atoms, but you don't complete the octet for the boron. It only gets 6 electrons through sharing. Right, now we can consider the other type of exception, molecules with central atoms with more than an octet. Okay. In principle, any nonmetal in the third row or lower can be a central atom with more than an octet. It has to be in the third row or lower, because we're going to put more than 8 electrons in these things. These things in principle, 8 electrons that fill the valence S and P subshells. Additional electrons, we will see, are involved with the valence D subshell, which only exist for atoms in the third row or lower. In other words, only nonmetals in the third row or lower have valence D subshells to form Lewis structures, or to hold electrons, so that it can form Lewis structures with more than an octet. Okay. Common exceptions with more than an octet are essential atoms: phosphorus, sulfur, arsenic, selenium, and tellurium. In addition, halogens like chlorine, bromine, and iodine are often exceptions. And if you see a noble gas like krypton or xenon as a central atom, those are always exceptions to the octet rule. So nonmetals in the third row or lower are full of possible exceptions to the octet rule. It's not as easy as seeing a beryllium or a boron compound as the case. It is not as easy as seeing a beryllium or a boron compound to identify this type of exception. Beg your pardon. Alright, so what does one do? If you think you may have a more than an octet exception, here's what you do. Do what you would usually do first. Draw a structural formula that shows how all the atoms are stuck together. Add up all the valence electrons. Use periodic table to help you. And then complete octets on all the outer atoms with lone pairs. Then complete the octet on the central atom with lone pairs. So in other words, do the outer atoms first, then the central atom. If there are still pairs of valence electrons left over, the molecule is an exception. Put all the remaining valence electrons on the central atom as lone pairs. Alright, these rules also appear in the text. Here are 4 molecules that you can try, which are exceptions to the octet rule. SF4, PCl5, BrCl3, and xenon difluoride. Notice this weird molecule. When you get a weird molecule like this, noble gas appears first in the formula and the name. I don't believe that's come up in the lectures before. This is xenon difluoride, for example. And I've already given you something you wouldn't have otherwise known. Each one of these things is going to violate the octet rule by having more than an octet on the central atom. Alright, attempt Lewis structures before moving on. Alright. When you construct SF4, you'll see that you have 2 pairs of electrons left over, and there are 10 electrons, or 5 pairs, on the sulfur atom. PCl5, when you drew the central atom as phosphorus and stuck 5 chlorines to it, it was immediately obvious that this would violate the octet rule. Here is the correct Lewis structure for PCl5. Here is the correct Lewis structure for BrCl3. Notice that there are 10 electrons, or 5 pairs, on the bromine atom in this case. And when you complete a Lewis structure for xenon difluoride, there are 2, 4, 6, 8, 10, or 5 pairs of electrons on the xenon atom through sharing. Alright, this concludes the second lecture for Unit 7.